After creating the algebraic method, Hess wanted to find an easier way to determine the enthalpy change of a reaction. What he did was he did calorimeter experiments to find things known as the standard enthalpy of formation, or delta HFs. The enthalpy change when a mole of a substance is formed directly from its elements in their standard states is known as delta HF. The standard state of an element is its most stable form at SATP. By definition, standard states have a delta H of formation of 0 kilojoules because that compound already exists at SATP. No energy is used to form it. See Appendix B on page 743 of your textbook for delta HFs of a bunch of different chemicals. You can calculate the enthalpy change of any reaction by subtracting the heat of formation of the reactants from the heat of formations of the products. Hess developed the following equation. Delta H equals the sum of the moles times the delta HFs of the products, subtract the sum of the moles times the delta HF of the reactants. This equation and the table on page 743 allows you to find the delta H of any reaction without ever having to do a lab. Here's example 1. Write the thermochemical equation for the formation of aluminum oxide. Now remember, formation equations, you form the compound from its elements and its standard states. So the elements in aluminum oxide are aluminum, which is a solid at room temperature, and oxygen gas. Now you have a choice. You have to balance this equation. I'm going to balance it to give me 1 mole of the product, which is the chemical that I'm interested in. That way, when I turn to page 743 in the text and look up the delta HF, I can just add that number to my equation. It's a negative 1675.7 on my table, meaning it's exothermic, so my energy needs to be added on the product side. Now if you want to balance the equation without using a half, then you have to manipulate your energy value to match the coefficient in front of the aluminum oxide. As a side note, in case you run across carbon, the standard state of carbon is graphite. If you think about it, it takes heat and pressure to change graphite into a diamond, so diamond is not the standard state of carbon. Example 2. Let's use the enthalpy of formation method to find the enthalpy change for this reaction here. This is the same reaction we did for example 1 of the algebraic method. You notice we'll get the same answer. That proves the equation works. To solve this question, plug into the above equation. A common mistake people make is that because we read from left to right, they will sub in iron oxide first. But the equation says products minus reactants. We're going to start with CO2. My reaction uses 3 moles of CO2. I look up the enthalpy of formation of CO2 on page 743. My reaction also makes 2 moles of iron, but because it's an element in its standard state, its delta HF is 0. For reactants, I use 1 mole of iron oxide. And 3 moles of CO2. Sorry, CO. I usually simplify my equation before I do the subtraction. There's a lot of negatives around. My reaction is exothermic, and it produces 24.8 kilojoules of energy. Pause the video here and try out example 3. Calculate the enthalpy change for the complete combustion of propane in your barbecue, and write the thermochemical equation. Here's the answer for example 3. Let's start by writing a balanced chemical equation. Propane has the expanded molecular formula CH3, CH2, CH3. We're going to do a complete combustion reaction. That means only CO2 and H2O are produced. Now, because this is a combustion reaction, the water will come out as a gas, because combustions are very exothermic. It's going to boil the water. That's important because you need to look up the right state of water on your delta HF chart. I'm going to start with CO2. It's my first product. My reaction makes 3 moles of it. Because oxygen is in its standard state, it has a delta HF of 0. My reaction is exothermic by over 2,000 kilojoules of energy. That's pretty hot. Because I have a negative delta H value, I'm going to add my energy as a product to my thermochemical equation. I don't have to manipulate this energy value. This is the energy change for my equation as written.